مرحبا طلاب، إن شاء الله تكونون بخير. راح أكمل chapter 4. Today I'll start parameters of a second order system on the S-plane. Okay. إيش معناته إنه I'm repeating twice system on the S-plane. إيش معناته إنه S-plane? As I told you before, S-plane is very important for us in demonstrating different phenomena, different idea. We'll understand it a bit by bit. And you remember that I said that for underdamped system, the roots will be like that. So we take the underdamped as a standard case because it's more commonly used in real life. And the roots will be S1, S2, it's a second order system, so we have two roots, S1 and S2, equal minus z to omega n plus minus j omega n times 1 minus zeta square under the square root. And we call zeta omega n, this one without the sign, zeta omega n equal sigma d. And omega n times 1 minus zeta square under the square root is equal omega d. And I told you omega d is the damped frequency. Okay? Now, these roots, I'm going to put them on the S-plane. This is the S-plane, you know, it's sigma and j omega. And this is the real part, which is minus zeta omega n. This is the real part, equal minus sigma, because we took sigma as the value without the sign. So it's minus sigma d. And this part, this one here, it's the j omega d, which equal j omega n phi 1 minus zeta square under the square root. Now, if you see that this part from here to here, and that part, which is, we can make a triangle if we take this part and consider it as it's here is the same. So if we, the pole from j omega d and zeta omega n is here. So if we take from 0 to this point, we have this line, which is omega n. Can you see that omega n, this is omega n, which is the natural undamped frequency, is greater than, you know, the قانون فيثاغورس في المثلث القائم الزاوية. فهاي عندي هذا j omega d أو هذا هو نفسه. This is zeta omega n and this is omega n. Omega n here, it's equal this one, zeta omega n كله square زائدا this one omega d square plus zeta omega n square under the square root. I'll get omega n, and of course omega n is greater than this one or this one. Okay, this is the S-plane مبدئيا as basic. If we look at this angle, the angle is theta with the x-axis with the sigma. Zeta is equal, if we take cosine theta is equal zeta omega n over omega n المجاور على الوتر, and it's equal to zeta. Then cosine theta equal to zeta. Cosine theta equal to zeta. Now, these are important things on the S-plane, which are going to be helpful later when we go on in the material. Now, if we have the configuration of the S-plane, we can find from here, if you see the S-plane, we define Tp equal to pi omega d. This is omega d. So if you have an S-plane with all these parameters and values on that's in front of you, you can find Tp, the time to the peak value. It's equal pi over omega d. That's omega d. Okay. And no, this is Ts, sorry. This is Ts. Settling time. The settling time is equal to 4 over zeta omega n or 4 over sigma d, the real part of the root. So if we have the imaginary part and the real part on the S-plane given to us as a data on the S-plane, we can find Tp and Ts. We can find percent overshoot from cosine of the theta, and from it we can get the percent overshoot. Now, if you see that Tp is equal to, I'll write it to here again. Tp equal Tp, as we said pi over omega d. So omega d, it's in the denominator. So then Tp is inversely proportional to omega d. horizontal line, horizontal time is of constant imaginary part time. Hence, TP is constant. Okay. So if we go here, let me talk here. If we have this as a plane, so if I have j omega d constant, so I can make a straight line here. All this straight line we have j omega d constant, right? So TP, this is the horizontal line which we are talking about there. The horizontal time is of constant. Horizontal, actually, let's say not time, line. Okay, this is the horizontal line. In this horizontal line, omega d or j omega d is the same, you see, or this side. And then TP here, it's the same. So line of constant TP. Now, if we have sigma d here, if we make a straight line like this, like Amudi, here sigma d is constant. So anywhere here, we have settling time which is equal 4 over sigma d, it will be the same, okay, because this is constant. So a horizontal straight line will give me constant TP, and I'll solve some question for you on that basis. What's the what difference does it make on the response? And the vertical line is for constant value of this line of constant settling time. I put them in colored pencil so that you can see. And from this, we make zeta equal cosine theta. So this is the line of constant zeta. Okay, every point you take here is the same zeta because we draw a line of theta, which is theta equal cosine theta equal to zeta. Okay, that's the meaning of the parameter which we are interested in second order under damped system. So now, what am I talking about? Look at this. They are only drawing. So if I have j omega g1 here, this is a straight line. We said that TP is constant. Let's call this TP1 because we call this j omega g1, and we call this j omega g2. And we said j omega g2, of course, greater than this, right? It's larger. It's here, and this one is smaller. So TP2 here, and if we calculate TP2 here on this line anywhere, because we have a constant j omega g, and if we calculate TP1 from j omega g1, so this is pi over omega g2, and this is pi over omega g1. So this, because this is bigger, TP2 will be smaller than TP1. TP2 smaller than TP1, right? Because we said that TP is inversely proportional to omega g. Because omega d is bigger, TP2 will be smaller. The same here. If we have, we said here, settling time is constant. Every vertical line you make, you have a settling time that's constant on that line. So we have TS1, and this is TS2. TS2 is bigger than TS1. And then, no, I mean sigma D2 here is bigger than sigma D1. So TS2 is equal 4 over this. This is bigger. So TS2 will be smaller than TS1. Okay? Now, here we have theta 1, we have theta 2. And this is for zeta 1, theta 1. And theta 2 for zeta 2. Zeta 1 is bigger than zeta 2. And then percent overshoot that I get from theta 1, which is, let's call it percent overshoot 1. And this we call it percent overshoot 2. Percent overshoot 1 is smaller than percent overshoot because zeta here bigger, so I'll get smaller percent overshoot. And zeta 1 here is bigger, so percent overshoot will be bigger than we said that as we get zeta bigger, we'll get less percent overshoot. So percent overshoot, because zeta here is bigger, you will get less percent overshoot than the other one, which has a smaller percent overshoot. I hope I got this right. So straight lines for constant TP. If you compare between two straight lines, so it will be TP2 is smaller than TP1, TS2 smaller than TS1. Percent overshoot, this one, because zeta is bigger, it will be smaller than percent overshoot for smaller zeta. Let's have, let's say, a straightforward example. Imagine that you are given this example. We have an S-plane. It have J omega D, so omega D equals 7 and sigma D equal 3. So we will find the other parameters that are missing. So what we find omega n, it's equal 7 square, that one. So this one is the same as this one. 7 square plus 3 square and equal 7.616. Of course, rad over second. Cosine zeta, zeta equal cosine theta, and cosine theta equal 3, this one, over omega n which we found, and it's then zeta we get 0.394, and TP, what's TP? It's equal pi over omega d. Pi omega d. You have omega d given here, so it will be pi over omega d and equal pi over 0.449 rad على second, and that's TP. Okay, TP. Now percent overshoot is equal to this expression which we have. It's E2 minus zeta pi over 1. There is a formulation for this in the book. You can have a look, but you can calculate it in your calculator directly. It doesn't need any more simplifying. So times it will be 26%, and settling time it will be 4 over this omega g, sigma g, and so it's 4 over 3. It will be 1.333 seconds. Again, notice that TP is smaller than TS, okay? Don't forget that. So if we have an S-plane with these parameters, we can get the other missing parameters. Like, so here, it's the line for the constant zeta, okay? And here, the constant, here if you like, constant TP. And this line is for constant settling time. Let's take an example, like we apply these fundamentals. It's like a design problem. The question is spring and rotating body and damper. We are asked to find D, missing, and J, so that settling time for this system will be 2 seconds and percent overshoot will be 20%. K is given, it's equal 5 Newton meter, okay? First of all, we have to have the model so that you can work on the model. So we have to find theta is the output, T is the rotational torque which you give to the system. So we should find theta of S over T of S. This is a typical example we have done before. Theta over T equal 1 over J S square plus DS plus K, and it's equal to I divided by J, so that to make the coefficient of this S square, make it 1 always, so that you won't make the mistake which sometimes a lot of students they make it. So it's 1 over J S square plus D over J S plus K over J. From this, we work on this, on the denominator, right? On the denominator. So what will we do? We'll have 2 zeta omega n equal D over J, right? And we have omega n equal K over J under the square root. So this is omega n square, and this is 2 zeta omega n from this transfer function. That's all we need from the transfer function. We can calculate all the other things from this. Always we also we have given that percent overshoot equal 20%. We can find zeta. How do you find zeta? Is equal use هذا a2 minus zeta pi zeta على 1 ناقصا zeta square تحت الجذر. Use this and from it you can find the zeta. This is known, it's 20%. Take away the 100, so it will be 0.2. So هذا equal 0.2. From this you can find by taking inverse exponential and you work on it, you'll get zeta. So from this we get zeta equal this, okay? So zeta omega n from the settling time he's given us equal to 2. So from the settling time we have zeta omega n, we'll get it, this is another information, equal to 2. ينتج omega n equal 2 over zeta, and هذا omega n equal k over j, which is we found it from here. We put here that omega n equal k over j under the square root. So now we have 2 zeta omega n. I got it from the settling time which he given me. Settling time equal 2, which is equal 4 over zeta omega n. So I get zeta omega n equal to 2. This is the data which I have. I am in data which is given to me, percent overshoot and settling time. So from the percent overshoot I get zeta. From the settling time I get zeta omega n. From zeta omega n equal to 2, I get omega n equal 2 over zeta and equal to تحت الجذر omega n equal k over j under the square root. ربع الطرفين we'll have k over j equal 2 over zeta كله square, right? From this we'll get j equal k over 2 over zeta كله square ويساوي لنا zeta square times k على 4. And put the data which you have. We have the zeta equal 0.456 square, and we have k which is given to me is 5 over 4. So I'll get j equal 0.2 قربتها 0.26 kilogram meter square. Okay شباب. Now I'll go back. I'll say this is I put 1 and 2. These are like خطوات الحل. I have 2 zeta omega n again equal d over j. So I got j, I got omega n, I got zeta. So I got d equal to 2 zeta omega n times j. And I have zeta, I have omega n was equal to k over j under the square root, which I can find. So it will be d equal to times zeta times omega n times j. And I'll put the value of, not the value, it's equal k over j, and I found k, I found j, so I can find the omega n, and this will give me 1.0316. And then the design parameter which we are looking for, j equal 0.26 kilogram meter square, and d equal 1.0316 Newton meter slash dash second. Of course you remember that this override over second, so مقام المقام صعدناه فصارت هاي second on top. I'll stop here for now, and I'll continue for another session, so I can finish the chapter 4. Okay, thank you.